Stanford University.
Nod yes, that's a good sign.
Oh.
Yeah, well, now that you're shouting.
Oh, okay. Welcome to EE380, October 22nd, 2008. Almost flipped the century here. Next week's talk is still to be arranged. However, November 5th will be Guido von Rossum from Google talking about App Engine. So you've only got 2 weeks left to complete your applications. November 12th will be Al Fazio from Intel talking about memory, which those of you who design computer systems have been very concerned about for probably your whole lifetime. November 19th, Tim O'Reilly, and December 3rd we'll close with the 23andMe folks. Today's talk is by the second of our MIT exiles. Notice how they come out here for winter.
Permanently.
Never go home.
Well, you know, winter, summer, you just get lost. Today's speaker is Carl Hewitt from MIT. And while he's done a lot of seminal work in the past, he sees a combination of events rushing at us that are going to cause great disruption. And, like all good MIT people, he seeks to find a single point of leverage to overturn to control everything. The particular point he's chosen is the particular problem is privacy-friendly internet applications, which by itself would be a revolution, even if nothing in the world was changing. However, in this talk, he's going to tell us about how he believes that restricted generality, solves this problem and goes through a couple of key arguments that he believes illuminate his decisions and justify them. However, I would ask one other thing. You say recovering rapidly. Cheaply seems to encompass more
Age.
Well, time can be money. So, thank you.
Thank you. Thank you very much. So how's the sound? Are we doing good? We're doing A-OK. Very good. Thank you. So anyway, the title's too long, so we'll just skip over it. Go directly to the cloud. So here we have the cloud, right? And of course, then we get Microsoft and Google, the guys who power this cloud. And what's the timing on this, Dennis?
You've got till 5:30.
Got till 5:30. Very good.
Remember that we asked questions.
Yeah, I will remember that you asked questions. That's right. So I'll leave some time for questions. So here's this amazing slide. And it does say privacy friendly, but also has this array of clients. Here we have the world's biggest client, a data center. How can a data center possibly be a client? Well, the cloud is very, very big. And by comparison, this data center is very small. So it's just one more client to the cloud. And the thing about the cloud is that in many respects, it's a kind of redundancy play. That you really don't want to lose your information. And from that point of view, this data center is a single point of failure. You can't have the information only stored there. It's also got to be stored in another client someplace on the cloud. And you remember the ancients thought, they ask, what does the world rest on? The world rests on a turtle. And what does that turtle rest on? It rests on another turtle. It's turtles all the way down. Well, the cloud is clients all the way up. It's just clients out there, folks. Some of their big, this is one of the biggest ones. Here's another one, a sensor client, just one chip basically, a rather small client. Here's a client grid, which our lives depend. Here's a client cell phone, and there's a client cell tower. So we've got all kinds of clients out there. And the thing is, what is this privacy-friendly bit? Well, there's going to be as much power, computational power in this thing, okay, in 15 years as there currently is in this thing now. So, this means that clients can do a lot. In particular, the client that you have with you, this guy, will be able to integrate the information out there, okay? And as long as it's got it integrated, right, if you can integrate it there, then you can store it encrypted out in the cloud, encrypted with your private key. So instead of trying to have these treaties between these enormous big guys out there to try to share your information, okay, you have your pieces of information out there and you integrate it on the client. And that's the way that we can get our privacy back, through cheap cryptography tricks. I don't know why I did that. Now, I actually already do a lot of stuff in the cloud. For example, these papers here. The PDFs for these papers are actually stored in the cloud in a Microsoft Live server. And one of them, this paper, instead of being a historical perspective, instead of being published in the communications of the ACM, instead it's published on Google Knoll, K-N-O-L, okay, which allows you to write reviews of it, allows you to make comments of it, okay, and it's a lot easier to get it published there than it is to go through the pipeline for the CACM. And not only that, but you can actually do a better job because you can make the article a little longer. You can actually have a couple formulas in the article and it won't get rejected. I can remember the days of yore when in the CACM you'd have articles like from Tony Hoare on communicating sequential processes, and Edgar Dijkstra on go-to continued harmful, and Bob Kowalski on algorithms equals, you know, a logic plus control, right? Now, these guys weren't always right, but they had something to say. It's very difficult to get an article that has something to say into the CACM these days. In fact, I haven't seen it happen for quite a while now. So this is interesting to see the transformations that happen. The cloud is a very interesting dynamic place. So what can we say about this cloud? It's a manifestation of what's happening to us, which is pretty incredible. We have the perfect disruption. We have a new hardware paradigm, we have a new software paradigm, and we have a new applications paradigm, all coming at us at the same time. The new hardware paradigm is this many-core architectures, which we are alleged not to know how to program. The new software program is client cloud computing, which the companies are alleged not to know how to deal with. And the new applications paradigm is this scalable semantic integration, because we currently live lives in silos. You've got your calendar silo. You got your email silo. You got your contact silo. You got your Word doc silo. You got your search results silo. And what's the integration mechanism? Cut and paste. And if you have an iPhone, you don't even have cut and paste. It's just incredible. Okay, so I'm going to be talking about this perfect disruption, talk about some lessons learned, and then talk about who wins. So, there's this paradigm, ORG's paradigm. And ORG stands for an Organization of Restricted Generality. And this is in contrast to my good friend Alan Newell, unfortunately he's no longer with us, who once invented GPS, the general problem solver. Taking note of some of Alan's experiences, we decided to aim low. Okay. So orgs are computer organizations, but people are integral to their operation. No people, no org. But they're also something technical. I'm going to talk about how they're also going to be an extension to the X86 architecture, which makes them very technical indeed. They operate according to principles and methods of authority and accountability, and they're distributed across systems, many core systems, data central, client, cloud. An org might have little bits and pieces in all of these. And orgs are not my invention. Orgs are an observation. Folks, this is what is happening now. You don't have to wait around for the singularity. It's already happening. It's just not the way that Kurzweil imagined. So this is actually what is happening now. Orgs have principles of concurrency, okay? They're obvious. We all know them. There's monotonicity, right? Once you leak something out on the net, you never get it back. There's message passing. Everybody knows that the internet works on the basis of message passing. There's commutativity, okay? That basically, you don't have to be there to catch the message. You can read it later, okay? There's a kind of commutativity between work and communication. And there's sponsorship. We don't do this for nothing, folks. There's pluralism. Nobody's in charge. There's skepticism. Don't believe everything you read. And there's provenance. Keep track of where these bits came from. It's going to be important when you get called to an account for them. So, it's basically message composability, interaction using messages. Now, this is different from the original conception of computation that we got from Edgar Dijkstra and that lot, and has now been transformed, which they believed in something called the global state. And this has been transformed into global state composability, and there are even people who believe that it might be the basis for a multi-core architecture called transactional memory. So how does a transactional memory work? The idea is that people are incapable of dealing with concurrency. So let each one of them continue to be the old sequential programmer that they were of old. And the system will keep track of everybody's reads and writes. And if it's not consistent, then it will magically grab you by the scruff of your neck, back out all the changes that you've made, and let you start over. Well, there are two observations to be made. One is that this only works in the address of one process on a single computer. And we are faced with problems bigger than that. The second one is this can be very inefficient. We're moving into an era in which you're going to have thousands of threads banging away inside a single process. What are the chances, what are your chances of getting all the way through this consistently before you interfere with somebody else? Back out, start again, and try again, and try again. So, what is to be done? Well, we'll turn Dijkstra on his head. He was a marvelous man. I used to argue with him all the time. So is global assignment considered harmful? We actually are going to have to change the way that we program. This idea that there's this big global state out here, and I've got these assignment commands, you know, with trillions of words of memory in it, and go plink, plink, plink on any one of these trillions of words that I want to, is just crazy. So what do you do instead? You can't go over to a functional world, because a functional world means that you affect nothing. We have to be able to affect things. But we have to do it in a very controlled way without the global assignment command. So what does that look like? Well, let's consider a simple auction, just to show you what it's going to take to program in this new realm. And this auction has a certain number of bidders. It has a current minimum bid, which keeps going up. It has a deadline, which is the time by which a bid, the next bid has to come in, or the auction's over, and the current highest bidder wins. And it has a record of the current bidding. So what you do is you have an alarm clock that tells you when alarm goes off, and if the alarm comes in before the alarm goes off before the next bid, another bid comes in, then the highest bidder gets it. So this is what it looks like. It says, if I'm getting an alarm message with a certain alarm time with it, okay, and here's a funny notation, it's a kind of functional notation. And what's happening is we've discovered what the fundamental data structure of the world is. It's not arrays, okay, it's not strings. It's XML, okay? We are going to compute using binary XML, okay? So this funny notation just means this, only it's arranged in a binary format. You know, it's too much to write this. Programmers will go crazy if to write that. So we'll write this. This is good enough. So if an alarm, when alarm time comes in, if the alarm time is less than the deadline, then you just do nothing, you return. Else, you tell the current bidding to process the outcome, and you return. So that's pretty simple. Now let's see what happens when a bid comes in. Well, if a bid with a certain amount and a bidder comes in at a certain arrival time, then if the arrival time is greater than the deadline, then you tell him, it's too late, Bunky. If the amount is less than the minimum bid, you tell him, it's too little, Bunky. Otherwise, you tell the current bidding the amount. You inform the bidders what the new minimum bid is and the new deadline. You send an alarm to yourself with a new deadline. And now here comes the part. You say, we'll return an acknowledgement to the bid and also become minimum bid equals the amount bid times 110%, and the deadline equals the current time plus delta. So what we've done is we've made a change to the world. But this is a very limited change. Who can we change? Just me. That's the only person in the world that I can change. For anybody else, I send a message and I say, please, and hope for the best. Does this sound like some circumstances you're familiar with? So that's the deal. No more global assignments if we're going to survive in this world in which we have thousands of threads tromping around inside the same process. Okay. Well, we're not going to leave this to chance. Okay. We're going to have the hardware enforce this new world, because otherwise, how can you know, right? I mean, they'll do crazy things, like in C++, they don't do bounds checks, right? If you make it optional, you're going to lose. So we're going to enforce the new world in hardware. And the way you do that is you have these little objects, like our simple auction. They can change themselves. And the hardware will enforce that you can't directly change anybody else. Those of you who are familiar with Lisp machines, days of yore, will know that the hardware used to do this before it got trampled by hardware that didn't. And now the hardware is going to have to do it again, because the many cores are actually going to force us to do this. We also have a problem with storage leaks. Now, in a multi-core system, reference counts are incredibly inefficient. Can you imagine all these many cores upping and downing the reference counts for this thing? It'll just use up the bandwidth, completely crazy. Garbage collection causes pauses. That's also totally unacceptable. So what you can do is we'll have the hardware fix this problem. The other problem that we have is one of locality. That because we have these little bits and pieces of storage that we're keeping around, you start getting holes in your memory system. And that drives your efficiency down like nothing else will. So what you have to do is you have to be able to compact the good stuff together. It's like if you didn't have a garbage can in your office and didn't regularly throw things out, pretty soon you wouldn't be able to find anything amidst the garbage. Same thing's true here on a computer system. Got to take the garbage out and compact the good stuff together. And also mobility. We got to pick up these orgs, they're running inside these machines, while they're running, and move them to another machine. Just like currently in VM, we can pick up a process while it's running and move it to another machine. And all of these things require hardware support at a very low level. If you try to do this in software, you will pay performance penalties ranging from 10 to 1,000 cost and speed. So what we have is we have to have hardware extensions for nonstop concurrent garbage collection, orgs migration, and support for objects. Because this is already the way that the world is going. This is the way that Microsoft goes with the CLR and its extensions. In fact, Microsoft has a project to put this kind of stuff into Windows 2011. They say, enough of this. We are tired of this. We cannot support this old legacy way of doing it. We're going to move the entire operating system to managed code, but they're going to need hardware support to do it. The JVM, same thing. Dalvik, which is Google's managed machine, and Tamarin, which is Adobe and Gazilla. So the job for the X86 is it has to do a good job of supporting all of these. And that's the future. But if you know how much we invest in the X86 architecture and how hard it is to change it, you'll know that the negotiations involved to do this are completely non-trivial. And also the underlying technology to actually do it is also not trivial. But that's where we're going. So, for the many-core architectures and the client cloud, basically orgs is where the center of the solution lies. Now I'm going to switch here and go to something called scalable semantic integration. And the challenge for scalable semantic integration, a big challenge, is inconsistency. So why is inconsistency such a problem? Well, there's a funny Latin name for it, but I like to call it IGOR. IGOR stands for inconsistency in, garbage out, redux. Redux means we do it over and over again. Okay? So what's the problem? The problem is, by the laws of classical logic, if you have a single inconsistency, then you can conclude anything. You can conclude the moon is made of green cheese. This is completely unacceptable. So say, well, them logicians, they're bright guys. Why would they put IGOR into the system? Isn't this dumb? Well, they didn't mean to put in IGOR. IGOR is a side effect of some other things that they thought were good ideas. It's like our software systems. We put in the good ideas, and then we discover the consequences and say, sheesh, we didn't know it would come to this. So this is what they had to. There is full indirect inference. Now this is indirect proof. If from psi you can conclude phi and not phi, then you have proved not psi. And this came because it was invented for mathematics, right? Mathematics is consistent. So if from psi you can include phi and not phi, the fault must be psi, right? Can't be anybody else. It's got to be psi. It's got to be the troublemaker. So therefore we've disproved him. Okay. But if you have that rule of inference, if you have phi and not phi, from not psi, we can conclude phi and not phi because we already have phi and not phi, right? But now we've concluded not psi, and we've concluded psi, and psi is the moon is made of green cheese, and we've derived that from a single contradiction. Oops. Then the other one is, if you have psi, you can include phi or psi. You say, what's the trouble with that? After all, if psi is true, then surely phi or psi is psi or phi is true, right? What's the problem? What's the problem? But if you have phi and not phi, From phi, we get phi or psi. That's disjunction introduction. Now we've got not phi, and we've got phi or psi. From that, we conclude psi. And again, we have green cheese from a single contradiction. Complete disaster. So what do we do? Well, we're software engineers, right? We know how to deal with problems like this, okay? We say, get rid of these two rules. We'll keep all the rest. Get rid of these two, right? And if you do that, then you get paraconsistent logic, which is a logic that's tolerant of inconsistencies. It says, okay, we'll just let P and not P lie there. They're not going anywhere. They're not going to bother anybody. Just let them sit. And so that's paraconsistent logic. And the idea is it tolerates inconsistency. So there's a system here done at Stanford. I work with the logic group over here. There's a very nice system due to Kassoff, Zen, Garg, and Genesrith called Predicalc. And what it is it's a spreadsheet that works on the basis of paraconsistent logic. So it's tolerant of inconsistencies. So you don't have to get the whole thing completely consistent in order to work with your spreadsheet. And there's another system I've developed called direct logic, which is based on natural deduction and has almost all the Boolean equivalences. There's a little star there. It means that, there's the 5% of them that you probably don't know about. So it's got double negation. It's got De Morgan's laws. It's got, whatever you care to name in terms of the Booleans. But, there's a little fringe element out there it doesn't have. And the reason it doesn't have them is it can't have them and remain paraconsistent. So it's pretty nice, and it does have abstraction and reification. It also has something that's very important, and that is we need a way to connect together the Boolean part of the world. See, this is implication. That's Boolean. Whereas this is provability. This means from psi you can infer phi. This means that psi implies phi. Got to have a way to connect them together. There's a classical deduction theorem. Okay, in classical logic, this one is equivalent to this one. If you can prove psi implies phi, that is equivalent to psi infers phi. No such luck in paraconsistent logic, but we have something that's almost as good, which is the two-way deduction theorem. It says that you can prove psi implies phi, provided that you can do two things instead of one thing. You not only have to be able to infer phi from psi, but also infer not psi from not phi. So that's basically just as good. We're within a factor of 2 of classical logic. So the problem was that paraconsistent logic was originally invented by these logicians on purely philosophical grounds. So they had their philosophical criteria. Whereas we software engineers have very practical criteria, We've got these software systems that are chock full of inconsistencies among the documentation and the use cases in the code, right? We just want to reason about this thing. We don't want to have some philosophical criteria get in the way. So they made some wrong decisions from our point of view. Philosophically, I'm sure they think that they're well-grounded, and then philosophically they're correct. But that's just irrelevant to us as software engineers. We need a practical reasoning system that's tolerant of inconsistency. Otherwise, we'll forever remain in this regime we're in now, where you have an operating system like Vista with its 50 million lines of code. And do you know what they use for specification language? Word documents. Joy. We got to do better, folks. We just got to do better. The hardware engineers are not, so stuck. They've got these enormous suites of things for verifying their hardware. What's wrong with the software engineers? We got to get with it, folks. Okay. So, there are some things we have to face up to. Let's talk about incompleteness and inconsistency. Incompleteness means that, your theory T is undecided. It's incomplete with respect to psi. It can't prove it and it can't disprove it. Inconsistency means it can both prove it and disprove it. Okay? So the logicians have done a marvelous job. They have invented ways for us to reason about incompleteness and inconsistency and discovered some amazing things using what's called the diagonal argument and the fixed point theorem. So here is the diagonal argument. Diagonal argument says, okay, I'm going to prove to you that you can't make a list of all the real numbers between 0 and 1. How am I going to prove that? I'm going to say, well, suppose you had a list. Write out the decimal expansion in binary of every number on your list. So F1 is the first number on your list, F2 is the second, F11 is the first digit of the first number, okay? Got your list ready? Good. I'm going to construct a number that's not on your list. The way I'm going to do this is I'm going to complement the first bit in the decimal expansion, the first number, the second bit in the second number, and now I have a real number that's not in your list. And you say, ho, ho, ho. I'll just take your number and put it in my list. And guess what I do then? I do the same trick. I construct another number that's not in the list. So you can't make a list of all the real numbers, because I can construct one using this trick that says, I'm not in your list. The other trick is the logical fixed point theorem. So what is a fixed point? Well, imagine you have a head of hair, which I don't. And on this head of hair, we're going to have a function that maps from the position of the root of the hair to the tip of the hair. The fixed point on your head is the hair that sticks straight up, right? Because the root point mapped to the tip point doesn't move. It's a fixed point. It's a fixed point. And back at MIT, where they teach scheme, it's called the Y Combinator. Okay. And there's actually a startup factory named Y Combinator. Now, why would you name a startup factory after the fixed point operator? Aha. The idea is you put this little group into the startup, you improve them till you can't improve them anymore, then they're a fixed point and you kick them out. Okay, so there's the trick. And now we're going to show that every one of these logical systems, this is Gödel's famous incompleteness theorem, is incomplete. We're going to construct this guy paradox sub t using the fixed point operator such that you can't prove it and you can't disprove it. So paradox sub t is the fixed point of diagonalize, where diagonalize takes in a formula, okay, and puts out, okay, the sentence that says, my input is the sentence S, my output is the sentence S is not provable. This should remind you of the diagonal argument. Because what this thing does is it says, what is paradox? Paradox sub t if and only if paradox sub t is not provable. So paradox sub t is the proposition, I am not provable in the theory T. Okay? And then you grind through a little proof. Oops. I'm missing a slide. Just a second here. I'm missing a slide. That's okay. So, a proof. There's a simple proof. It's probably in the next, is it here? No? I'm missing a slide. Okay. There's a simple 5-line proof of this. You know, Gödel had this great big long paper to prove it. But there's a simple 5-line proof of this. And it's simple enough that it's probably mechanically discoverable. The proof is so simple. But anyway, here's the deal. So we can paraconsistently prove First of all, paradox sub t, if and only if not paradox sub t, that's by the fixed point operator, says I am not provable. You can't prove it, you can't disprove it, and we can prove this all in the theory T. But now, you look at this and you say, sheesh, I can prove this. That's logically equivalent to this. So I can prove this, and that's inconsistent with that. So we have just proved that all these theories are inconsistent. They are all inconsistent. Now, it's a good thing we're in a paraconsistent logic, otherwise we'd have green cheese, right? So what's the deal? The deal is the laws of thought are inconsistent. How did we get into this situation? Our information systems are chock full of inconsistencies. We want semantics, so we use paraconsistent logic. So we say, we don't care. This bug is a feature. We don't care that every theory is inconsistent about this. It's not going anywhere. So inconsistencies are a fact of life. Not only is the web full of inconsistencies, not only are all of our software systems full of inconsistencies, just by pure thought alone, I can sit here and derive an inconsistency. We've got inconsistencies galore. So what does this mean? It means that we're in for a paradigm shift. Instead of being in the consistency maintenance business, we are in the rapid recovery business. Okay, so we want to talk about scalable semantic integration. Inconsistency is a fact of life. What does it mean in practice? Well, let's talk about practical semantic integration. So here you are out here working for the ABC Corporation. We are got a joint product with the XYZ. We're ABC. We've got a joint project with XYZ. This is before the downturn, mind you. Sales are going like gangbusters. And we need to reward the joint sales teams, okay? So we got 60 regional sales managers from both companies. Going to include the international ones. We're going to have to get visas. It'll be summer 2009 in the western U.S. We're going to have a joint sales conference. I'd like to be in a scenic location near golf links. Have an awards banquet. We'd like to have individually engraved plaques. Don't know exactly how you do that, but we'll Google it and see what we can find. There ought to be somebody that makes engraved plaques. Sales vice president of both companies must attend. These are busy people, so that's a constraint. We'll do that. We're supposed to be efficient, so we're going to try to coordinate the air and the car rentals to maximize interaction, figuring that, you know, if we can promote more synergy between the sales teams by having them travel together and the rental cars or on the planes, that'd be a good thing. We're budgeting $200K, but there's a downturn on, and this budget might get cut. So be careful about down payments and contingency fees. And the vice presidents want a detailed proposal in 1 week from us, please. Right. And we're going to solve this problem using cut and paste. Right. We'll outsource it, right. Joe in Bangalore will solve this one very well. So you see what our problem is. You see what our problem is. We're pulling in information, okay, from the web, from our internal databases, and we got to get, a little bit of information from the other company, right? So good luck to us. So what does that mean? That means we've got some requirements. Somehow we have to come up with an intuitive semantic user interface for this thing. We're also going to need a scalable semantic engine. And by the way, there was something called the semantic web, where all this was supposed to happen, by manually marking up the stuff. Forget about that. That's never going to happen. Okay. But that's the deal. That's what we have to do. That is our challenge. Now, we do have a system called OWL. OWL stands for Ontology Web Language. Okay? But it's got some issues. One thing is that the way it currently stands, an OWL tool ontology must be absolutely consistent. We don't think we're going to be able to live with that one. So we got to switch this thing over to Paraconsistent Logic. Also, OWL tool supports only one ontology or theory at a time. We don't think we're going to be able to live with that one either. One ontology for the world or at a time. I mean, we got ABC Corporation, we got XYZ Corporation. Who knows how many ontologies they've got? We've got at least several thousand. One at a time, just not going to make it. And also, OWL tool does not support abstraction and reification. In order to do those proofs of incompleteness and inconsistency, we had to be able to go back and forth between text and propositions. You see, diagonalize takes in text, okay, converts it into a proposition, and then converts that back into text. We actually use XML. It's structured text, but it is text. So you need this ability to go back and forth between text and which is just text about the world. You conjure it up, you drag it in off the web, somebody types it in, and propositions, which are things that you reason about. Okay. So you need some way to take in text and abstract it into propositions. And then when you want to communicate with some person, you got to take this proposition and convert it back into text. So that's an essential kind of operation that we're going to need for semantic integration. And unfortunately, OWL tool doesn't have that. So we've got to add that in. There's an additional bigger problem that I've been showing you these logical formulas, right, with implication and conjunction and inference, right, and turnstiles, right? That's not going to work for the general population. They're going to be typing in the language that they know, like English or French or Chinese, right? Okay. So, our semantic integration system, okay, has got to speak that language, right? So that means the natural language, okay, has to be importable into this next generation of OWL. And they're nowhere close to that. Now, fortunately, all is not lost, because we can make these extensions, okay, without having to completely redo the work that's currently been done with OWL, in which we can preserve their existing ontologies, the work that's been done with those ontologies, right? So that's a good thing, right? But we do have a pile of work ahead of us. Okay. So here we are. Here's our perfect disruption, what's coming at us. The many-core architectures, the client-cloud computing, and the scalable semantic integration. What can we say about lessons learned? Well, we do indeed have the perfect disruption. You know, all our technologies are getting turned on their heads. The X86 is getting extended is going to get extended for the many-core. The laws of logic are being revised to tolerate inconsistency. And OWL 2 needs to be revised and extended. So what's to be made of this? I think the primary lesson learned is humility. We don't know much. Some of it's wrong, but we don't know which parts. And that's just the truth of the matter. You might as well face up to it. Where does that leave us? What to do? It's progress, not perfection, in our game. So we must be brave. So we will have new products. So here's academia up here. This is the academic box. We've got theories of concurrency. We've got information theory. We've got the guys studying human factors, all doing great science and research. Down here, we have the technology box. We've got billions of dollars pouring in, billions of dollars, tens of billions of dollars into the many-core, into the client cloud, and into semantic integration. So here are our new products boxes. There's hardware acceleration. The hardware has got to get accelerated, okay. And what that means is there's concurrency theory feeding in here and the many cores. And that's in turn going to feed into the clients in the client cloud. And then there's the semantic enhancement box where we have semantic integration feeding in and concurrency theory, information theory, and human factors feeding in to this box. And then, of course, this goes in to the client cloud. It's a basic schema of where we're going. So we have mission statements from the usual suspects. Microsoft, software for computers on every desk and in every home. So software. Google, organize the world's information and make it universally accessible and useful. Information. Yahoo, connect people to their passions, their communities, and the world's knowledge. People. This goes right back to the roots in their name. See? Software. Google, big information. Yahoo, yodeling to people. Very consistent. Now, this might remind you of the three blind men and the elephant. Except this elephant is different. Because every 2.5 years, this elephant gets twice as big. And it keeps doing that over and over again. So I actually have enormous respect and admiration for these companies dealing with this exponentially growing elephant. It's amazing that they are able to cope with this dynamically changing situation. So where do we stand? Well, in terms of semantic enhancement, which is where these guys are going to rely on the hardware acceleration, but these three companies, it's semantic enhancement. You'll notice that Microsoft has bought PowerSet. Amazing. For a non-trivial piece of change, which is widely rumored, but not confirmed to be around $100 million. So they are positioning themselves because they know that we're not going to, the people out there are not going to be typing in these logical formulas. Just crazy. It's got to be natural language, right? And PowerSet has excellent natural language technology. Google, You notice that the Google interface keeps getting smarter, the search interface. It's got these remarkable pull-down menus, which has all these things. You type one word, and it starts typing words after that that semantically make sense. Where is all this coming from? And you type in, it knows about people's names. It knows about locations. It knows about the World Series, right? Knows about all these things. So semantics is creeping in to the Google search engine. And then there's Yahoo. And now Yahoo has enhanced search results with markup. So you can type in kids movie, right? And in your Yahoo search results, Toy Story pops up. But this is not an ordinary search result. There's a picture of the robot in Toy Story right there in your search results, right? And in your search results, you typed in, kids movie, you got a search result, and there's a button there that says reserve now, okay, on Netflix, okay? And this is in your search results, right? So, it kind of knew a little bit about kids movie, didn't it? The other thing they're doing, which is totally amazing to researchers and companies, is they're saying, well, we're not #1 in search, says Yahoo. So what can we do as a game changer around here? Well, there's a big problem for innovation in search. It's called $200 million in 10 years. And that's what it costs to build a competent back-end search infrastructure for the web. Okay, $200–300 million, 10 years. Most startups don't have that. Stanford doesn't have that. But Yahoo says, well, we have this new program called BOSS. We will give you access to our back-end search engine so that you can innovate the front end and see if we can't change the game around here. So these are exciting times. So there we go, some lessons learned. And now the question is, who wins? And we all win. And how do we win? Well, IT has the potential to become easier to use with civilized discourse, more useful because of semantic integration, not having to live the life of the silos, and privacy friendly because of client integration. The clients are powerful enough to integrate the information, which means that you can store your information in the cloud safely because it's encrypted with your private key. And there are cryptographers that can play even better games than that. But anybody can understand this, that if you've got your information stored in the cloud with your private key, when somebody comes with subpoena, the divorce attorney, the FBI, the Chinese censor, to Google doesn't have to be evil anymore. Google says, sure, take it. It's yours. Of course, if you want to read it, go talk to the client for his private key. Good luck to you. Here's the information. It's yours. Okay. And after the current crisis is over, right now we're headed down. Think of this as the upside of the downside. Employment will increase because we're going to have these new creatures called ontologists, okay? Because we're going to have to ontologize all of this information out there, okay? Right now, we have people, tending these webs of information, but they don't know what they have on board, right? Soon they will have truckloads of ontologists, so they will know what they have on board. We'll have orgs technologists, because as this technology moves deeper into the organization, there's going to be opportunities for screw-ups like you wouldn't believe. All the things that Dilbert talks about as happening between the people, now going to happen deep in the bowels of the machine. And there's no way to stop it, because this is the only way that you gain efficiency and scale. It's the only way. And we'll have discourse experts, because they begin to figure out that if we want to have people using these machines, you're going to have to talk nicely to them. No more of this hourglass spinning, spinning, spinning when you tell your system to shut down. You say, why won't you shut down? You'll say to the machine, why won't you shut down? It'll say, oh, well, I'm trying to, it'll come back to you and say, oh, well, zone alarm's not shutting down. And you say, okay, how long do you think it's going to be before you shut down? And it'll tell you, right? These days, okay, doesn't matter how hard you pound on the table. The hourglass just spins and spins and spins. And there'll be a lot of revenue to be gained from this. So where are we? We're going to the cloud, and it's going to be orgs combined with semantic integration that basically lies in our future. So thank you very much. Questions, comments? What do you think? Les Ernest, you've been around a while.
Well, you didn't mention it, but it seems to me you're dealing with a giant time-sharing system here. Namely, the internet.
It's a funny time-sharing system, because when you say, you know, I'd like to do a search on google.com, do you think it goes to the mighty time-sharing system at some location? There are edge things out there. There are little data centers all around the world. Google won't tell you where they are. So the cloud, okay, is an amazing thing. Okay, there's this thing called google.com that you're talking to, okay, but it inhabits the entire planet.
Yes. But it is nonetheless a time sharing.
It's a resource sharing system, right? Right. Now, there's offloading that's done. For example, peak search time in the US is different from the peak search time in India. So there's planetary load balancing going on.
But that's been happening for many years.
Yeah, but this is all happening off of a single URL. So yes, we do have, I wouldn't say we have a time-sharing problem. We have a huge distributed systems problem. But the thing that's new about it is that now on your cell phone, in 10 years, you're going to have a distributed system living there with representatives from Google and Microsoft and Yahoo and IBM and Amazon, right, and Sears, all living on your cell phone. So if there's a time-sharing system, it's in your pocket.
Well, you just moved all the turtles into my pocket, essentially.
Well, that's just, it's clients all the way up, right?
Yeah.
So you have a client in your pocket, right?
And
it's talking to all these other clients that are talking to all these other clients. You got this network of clients out there. It's clients all the way up.
But it's also all in my pocket. Because
now, the thing about your pocket is you don't store anything permanently in your pocket. You might drop the thing in the swimming pool.
Yep.
The stuff in your pocket is cached there. It permanently exists in the cloud where it's safe, redundantly stored, right?
That's why it can all be in my pocket.
That's right. You can cache, right? Just about everything you know it can be cached in your pocket, but it's only cached there. It's not permanently stored there. That's not the only place it's stored.
But I can't tell the difference, so that's why it's all in my pocket.
That's right. Well, it's all responsive. I mean, it's downloading stuff, because the stuff in your friend's pocket is also coming over into your pocket dynamically in real time, too.
Yeah.
And your stuff is going over to him.
Mm-hmm.
So now we got a pair of pockets. And then you're a member of XYZ Corporation. Some of it's back there, some of it's down here. So what the cloud says is where it's physically located is just a performance issue. Just a performance issue. Yes?
Just because it's in your pocket doesn't mean it's going to be private with the operating systems we have today.
Oh, well, that's true. That's true. And that's why we need extensions to the X86, right? Is because there's certain things.
The X86 privileged architecture was just fine. They didn't use it.
Yeah, that's
but
true.
Making extensions doesn't solve the problem.
We weren't desperate enough. Now,
That's right.
Now, with the many cores, we're desperate. You see, you're not going to make an extension to the X86 unless your back is to the wall and there are guys out there with guns and bullets that say, you got a choice. You can change or you can die.
I see no evidence that they're moving in the change direction.
Right. Well, you have to talk to the guys who make these things. Yes, Dennis.
Carl, you said that you have a client in your pocket that somehow is connected to the cloud, and that you get reasonable bandwidth out of this. How do you do that?
Well, I mean, bandwidth, it's a phenomenon like Moore's law, that bandwidth does go up. And as long as you cached enough of it, and as long as you've got the thing connected while you're sleeping, so it can be hauling down stuff, okay? Maybe, when you're sleeping, it's actually plugged into a wired port, so it can even get greater bandwidth while you're sleeping. So while you're sleeping, it's communicating. And as long as you have enough of it cached in your pocket so that in real time you don't have to drag down very much, then it's like cache memory, it's like virtual memory, okay? You can afford to take the occasional hit. You can take a cache hit, you can take a page hit on a virtual memory, you can take a communication hit on your pocket client where it's got to go out and drag something down now, as long as you don't have to do too much of that.
Well, but even if you have that cache,
it's a big one.
And you're using information which is not part of the local object that you're working on.
You're not working on one. I mean, you're not working on one object. I mean, you will have hundreds of millions of objects in your pocket, if not soon billions.
I'm only thinking of one, and that one object communicates by making messages to other objects.
They'd almost all the time that the object it's communicating to had better be in your pocket.
Yes.
And you want to talk to Amazon? We have a representative from Amazon in your client, right here. We don't have to go out the net to talk to Amazon. He's right here.
But the fundamental Amazon database is not.
But how much of it, the question is, how much of it is being used new? How much of it have you already used? It's already cached locally.
And what is its consistency state?
Now we've given up on consistency, haven't we? We are into rapid recovery.
I see. So that if I order a book, and the book has not been published yet, or was published and is out of stock, that's something that gets fixed up later.
That's true. That's what happens now. And what Amazon can tell you they sold you a book, this has happened to me, and then say, oops, sorry, we friendly guys have canceled your order. Sorry about that. And I also, they apologize, I try to get on an airplane, right? They say, sorry. We've changed size of planes and your seat no longer exists. So yes, so you're in business, right? And you're in business and you try not to disappoint your customers to the point that it's unprofitable. But you can be a lot more efficient if you disappoint some of your customers some of the time. Now, there might be some penalties and promotions, etc. Amazon might give you a gift certificate for 10% off on your next book. Okay? The airplane might give you a free ticket to Timbuktu, right? So there's ways of, sweetening the apology. But not trying to run on the basis of absolute consistency is more efficient for the economy. Question?
Yeah. So about the paraconsistent logic, so what level do you kind of see that coming in? Would that be sort of enforced at low levels, and then kind of regular software engineers would just be kind of programming sort of oblivious to that, or would we actually be kind of using that in our everyday sort of lives?
Well, yeah, what we have to do is we have to make tool sets for software engineers based on paraconsistent logic. So we have to teach, instead of teaching the software engineers classical logic, we'll teach them paraconsistent logic.
Okay, right. It looked pretty complicated. So
classical logic is also a little complicated, but this is a subset of classical logic. There are 2 rules less to learn. That's the good news, right? Question?
I can kind of see how, when you were working out the proofs, that when you get colliding terms that are inconsistency, you can just ignore them and let them sit there. But how do you envision dealing with incompatible whole ontologies or whole frameworks? Because, like this company, ABC, has a whole different way of thinking about stuff than XYZ.
Right.
And they don't map onto each other.
Right.
How do you envision
Yeah, you notice that the inference, the turnstile that says this infers that, always had this little subscript T on it?
Yes.
Mm-hmm.
That's for the theory T. So for T, we can substitute Amazon, we can substitute Bill, we can substitute my wife, we can substitute yesterday. These are all theories, and you have to be able to reason about multiple theories.
You didn't show any formula that had multiple theories.
That's true. They were all parameterized. They were all parameterized with T, right?
How do you get them together?
Right.
Are there any rules for getting multiple?
There's a whole art form to that, which is a whole other lecture.
Modal logic. So there's some
Well, no. Modal logic is something. No, modal logic speaks of things about necessity and possibility, right? Here we're talking about.
defined in terms of
I think
universes.
here we have a theory, theory, sub Hewitt. This is what I think, okay. Then we have sub Allison. This is what Dennis thinks. And then in my theory, I start talking about things in his theory. And in his theory, he starts talking about things in my theory. So that's just another way in which OWL2 has been extended. The semantics of OWL2 only cover one theory, right? It has to be that you can talk about multiple ontologies at the same time.
Are you equating ontology with theory?
Yeah, ontology equals theory. Ontology is just another way for another name for theory.
Any other questions, folks?
What do you think, Jeremy?
What are your predictions, Al?
Predictions? Well, I'm looking for the upside of the downside. It looks like Microsoft and Google, okay, and Yahoo, right? But Yahoo's got a few organizational issues right now. But they too are all moving in this direction of semantics, right? And with the hardware moving toward the orgs, okay, it looks like something like this is pretty much inevitable, and what we don't know is the time scale over which it's going to happen.
No predictions on time scale?
Predictions? What are your predictions on time scale, Jeremy?
Let's see. Following the downturn.
Following the downturn, right? but that's the thing, you see. In terms, the funny thing about this downturn is that there's a lot of fluff that's going to get taken out of the system, okay? And Microsoft and Google, and even Yahoo, can create the cache to do this. It doesn't require an extraordinary amount of cache. And with the flaky startups, okay, shedding people, they'll actually be able to hire people to do it. So this could actually happen a lot sooner rather than later. Because you'll have the people, and these big companies have the capital and the incentive.
Right.
So it really could happen sooner rather than later.
Think it'll save the valley?
I don't think it makes much difference. We'll all be saved. Anyhow, thank you all very much.
Yeah, thank you.
We'll see you next week.
Yeah.
For more, please visit us at stanford.edu.